Alright, so for the second moment, so in this video we're going to talk about the moment of inertia for areas, or the second moment of inertia. Please note there's something called the mass moment of inertia, which is used a lot in dynamics classes in terms of like the rotation of bodies, but we're not going to be talking about mass moment of inertia here. We're talking about moment of inertias for area. So the second moment of inertia may be thought as a body's resistance to deflection due to shear loading or bending torsional moments. So if you have let's say for example, you have two beams. Alright, we have two beams that are fixed to a wall. Alright, we have one beam here. Alright, that has a cross section of a very thin thickness, and it has a very tall width here. Alright, and then we're going to have a second beam that'll have of the same dimensions. Alright, so it'll have the same thickness, same width, but it's going to be rotated 90 degrees. So to both of these beams, what we're going to do is we're going to apply a load at the end of the beam. Alright, both of these beams have the same length. Alright, and what will happen is they'll experience different behavior. So these forces P are going to cause the beams to bend. So in the case of our first case, we only notice a very slight bend in our beam due to that applied force. Right? And we'll call that deflection. Alright. So for our second case, our deflection is going to be a lot larger due to that applied force. Alright, so that change, or that deflection, is going to be proportional so in this case what we notice is that delta 1 is going to be less than delta 2, and then the amount of deflection is going to be proportional to something called the moment of inertia, or the second moment of the area, which we're going to denote with a letter I. And the moment of inertia in this case is going to be greater for case 1, much greater for case 1 than for case 2. Right? So since the moment of inertia is greater for case 1 than case 2, we're going to have a the stiffness, or the amount of deflection, for case 1 will be less than in case 2. So the stiffness is going to be greater for case 1, which means for the same load and the same length of the beam, it will deflect less than it would for the specific case. or for the second case. All right. So in order to calculate this value I, all right, we need to use the following set of equations. So if we have our coordinate system, our xy coordinate system here, and we have a cross-sectional area of our beam, our structure, we can have a very small element of that cross-sectional area, which we'll call dA. All right, and we know that the center of that area we can define using its coordinates x and y, and we can also define it relative to the origin using a radius term. All right. So what we can say is that the moment of inertia of that little element would be equal to about the x-axis would be equal to proportional to y squared times dA. If we integrate that, we would get I of x would be equal to y squared dA. And then if you look at, we do the same process, but the moment of inertia about the y-axis would be equal to x squared dA. And then we could integrate that. And then for the moment of inertia, which is the ability of a body to resist torsional twisting, it would be equal to r squared dA, or you can think of it as just being equal to I of x, which should just be I of x plus I of y. All right. So those are the integral formulas to determine what are the moment of inertia about the x, y, and z axis. And the last thing I'll note is that since we have all the squared terms here, moment of inertias will always be positive quantities. Alright, so that concludes this video on moment of areas.